Okay, in this video we're going to be talking about measures of center of a data set. Now, I've listed some heights of students here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 students' heights, and this is in inches. So this student is 62 inches, this student here is 60 inches, and just a reminder, there are 12 inches in a foot, so this student here is 5 feet tall, this student here is 5 foot 10, etc. Now, suppose we want to encapsulate this data into just one representative number. I've given you 5 choices. We're not going to work out anything in particular for these, but out of these 5 choices that I'm giving you, which one do you feel represents this data set the best? 66 inches, 73, 80, 52, or 60. So pause the video now, have a quick think, just how you feel about it, which one represents these numbers the best, and then we'll talk about it. Okay, now that you're back, I feel most people have chosen 66. And the reason is 66 tends to be somewhere in the middle of this data set. There are some numbers bigger than it, like 70 and 73. There's some numbers smaller than it, like 62 and 60. It's sort of in the middle. 80 isn't a good representative. It's much bigger than the elements. Same with 52 in the way that it's much smaller than the elements of our data set. And 60 and 73 seem to be more towards the extreme elements of our data set. So the one in the middle seems to be our best representative. And in general, we like numbers that are in the center of a data set, somewhere in the middle, to be representatives of the entire data set. We're going to talk about 3 of them. We're going to talk about the mean, the median, and quickly we'll talk about the mode as well. First, I want to talk about, in some sense, the most common measure of a center or measure of central tendency, called the mean. So the way to think about the mean, there's kind of 2 ways. You can think of it as the fair share, or you can think of it as the balance point of the data set. And let me kind of explain what I mean by both of these. So we have this little example here. So let's say it's a 5-element data set, 1, 3, 4, 5, and 7. You can imagine that these are represented by the following dots, 1 dot, 3 dot, etc. Now, if I took all of these dots, combined them together, and shared all of the dots evenly over the 5 different data points, well, there's 1 plus 3 plus 4 plus 5 plus 7, 20 dots. I want to share them over 5 data points, so 20 divided by 5 is 4. So each data point gets 4 dots. So we're saying the mean of this data set is indeed 4. The other way to think about this is as the balance point. So imagine that we plotted our points on a number line. So 1, 2, 3, 4, 5, 6, 7. And we wanted to put this number line on a little wedge, on a wedge so it would balance. And where would it balance? Or it would balance right at 4. So that's another way you can think of the mean as the point where the data set would balance if you plotted all the points on a number line. And just some notation here. So for a sample, let's call the sample x1, x2, all the way up to, let's say there's n members of our sample. We use the notation x bar, an x with a bar over it, to mean the mean. And that's just the sum of all of our data points, our n data points, we add them together, and we divide by the number of data points. Another way of writing this, you can see it in sum notation as well, summation notation. So rather than writing this long string of x1 plus x2 all the way to xn, well, what am I doing here? I'm adding up all of these x's where the subscript here ranges from 1 to 10. So we can use summation notation for this. And so I'm just going to write this in summation notation. So let's say I'm going to call the index I. So the index here will be I. So I'm adding up a bunch of these xi's. And I goes from 1 to n. So this means the same thing. The sum of xi as I goes from 1 to n, that's exactly this here. So I want to divide that by n. So if we have a sample of n data points, we write it as x bar, and we calculate it the way that you expect. Add up all the data points, divide by the number of data points. And if we're talking about a population mean, these are a lot harder to know because you would have to figure out the values for all data points in your population, divide by the number of data points in your population. That is usually really hard to find out. But the notation we use for that is this Greek letter mu. It's kind of like a U with a longer front here. So that's the population mean. And most times we're not going to know this, or if we know it, it's because of some mathematical reason. Usually we're going to calculate means of samples and use that as predictions or estimates for the population mean. Let's move on and talk about the next measure of center. The median is a measure that just talks about the order of a data set. So in some sense, the actual quantities of the number don't matter as much. It's more so in what order the data set is once you've ordered it from least to greatest. And the median, it's kind of in the name, it's the data point in the middle. Now, if you have an even number of data points, then you're going to have 2 in the middle. So you just take the average of the middle 2, and we'll see an example of this. There's a nice helpful way to figure out which data point you need. And if you have a really large data set, this is more helpful. It's harder to count. So if we have n data points, just figure out what n plus 1 over 2 is, and that tells you which data point, once they're ordered, is the median. And of course, sometimes you'll calculate a 0.5, and in that case, you would just take the average of the 2 surrounding that. Let's do an example to see what's going on. I have this data set here. This happens to be ordered. Maybe you'll get a data set that isn't ordered, so you'll have to order it yourself, but this data set is already ordered. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements in this data set. So we want the median. Let's use our little formula here. This is a small data set, so you could just kind of count. But let's use our formula. We want the median, and we're going to use the symbol M for a sample median. I'll write that down in a second, a sample and a population median. So it's going to be the 10 plus 1 over 2th data point, which is 11 over 2, which is the 5.5th. So I got this 0.5 calculation here. So this means I want the average, or the mean. Let's say mean instead. Let's say the mean of the one below 5.5, so the 5th, and the one above 5.5, so the 6th, immediately above and immediately below. So let's figure that out. We have 1, 2, 3, 4, 5, so there's the 5th data point, and there's the 6th data point. So we have 9 and 11, so I want the average of those. I think you can easily see that that's going to be 10 in the middle of 9 and 11, but if we wanted to calculate that, M is going to be 9 plus 11 over 2, which is 10. So our median, our sample median in this case, is 10. And just quickly, I'll just do this in a little box over here. So for a sample median, we use the symbol M. And for a population median, which isn't going to come up a lot in this course, but it will in future courses if you take more stats, you use this Greek letter. Let's see if I can draw it. Eta. It kind of looks like an N with a longer right tail. It's called eta. But we'll focus mostly on sample medians. All right, let's do a little calculation to make sure we understand how to do this. So try and find the mean and median of the data set that was in the first slide of our video. Remember, this is just heights of 10 students. So pause the video now and try it yourself. See if you can calculate the mean and the median. Okay, now that we're back, let's do it. So remember, the mean, it's going to be a sample mean. Well, we just want to add up all of the numbers in our data set and divide by the number of data points we have. So we're going to add up 62 plus 67 plus 71 plus 65 plus 69, etc. I'll just put some dots there, but hopefully this is clear what's going on. Plus 62 plus 70, and we have 10 data points. And you can check that this indeed adds up to 661. So we need 661 divided by 10, and dividing by 10 is easy. I don't even need to bring out my calculator. It's 66.1 inches. So the mean height is 66.1 inches. Now for the median, well, I need to order this data set. So I'm going to pause the video myself. I'm just going to write it down ordered just to save a bit of time, and then we can talk. So here's our ordered data. I just took this data and ordered it from least to greatest. So note that we have 10 data points here. So the median is going to be 10 plus 1 over 2, so 5.5. So that's going to be the average of the 5th and 6th data point in order. 1, 2, 3, 4, 5, 6. So the average of these two is our median. So 65 plus 67 over 2 is 66. A quick discussion about mode. So mode is the value that occurs most often in a data set. In the previous data set that we looked at, you saw that 62 occurred 3 times. So the mode of the previous data set was 62 inches. In practice, we don't use mode too much, but we do talk about modes of histograms. We'll call these distributions later on. But imagine that these are histograms. And imagine there's lots of bars in these histograms. And I'm not drawing the bars entirely, I'm just kind of drawing the tops of them. So really, you're thinking of these as really small bars, like this. But both for the sake of clarity and because I don't want to spend loads of time drawing bars, I'm just going to draw the tops of the histogram, kind of how they roughly look. Hopefully that's kind of clear. Okay. When we have a histogram or a distribution that kind of has just one bump, we say it's a unimodal distribution or a unimodal histogram, and the mode is here. So this is unimodal with this mode. Some distributions or histograms have more than one mode. We say they're bimodal or trimodal or whatever. Here's a histogram with again, we're thinking of this as the tops of lots of bars of our histogram. So this is bimodal. So we have one mode here and a smaller mode here. So we're thinking of this as bimodal. And then maybe some data sets don't really have a mode, so they're non-modal. This one really doesn't have a peak where most of the data occurs, so we would call this non-modal. And I don't want to say too much more about modes other than that. A quick note about this idea of skewness. And skewness basically talks about if the data set is kind of shifted to one side or the other. And the mean and the median are kind of affected by this. And let me give you an example here. So means, if you think of the balance point idea of means, they're going to be heavily affected by really large or really small values in a data set. And we call those outliers. So outliers, we're thinking of extremely big or small. Elements. And here's an example here. So let's say I took a survey of the number of children in 6 different families. And I found that 2 families had 1 child, 1 family had 2, 2 families had 3, and there was 1 family that had 16 children. And if we figured out the mean of this, well, that's going to be 1 plus 1 plus 2 plus 3 plus 3 plus 16 over, though there's 6 elements. And if we add that up, we get 1, 2, 4, 7, 10, 26. So it's 26 over 6, which is 4.33, 4 1/3, really. And you can see that these 5 families actually have fewer children than the mean, and only 1 has more children than the mean. This is heavily affecting the mean. Of course it is, because it's way larger. So this data set is in some sense skewed to the right. The median, if we calculate the median, which we'll do here in blue, the median, well, that's just going to be, we have 6 data points, 1, 2, 3, 4, 5, 6. We're going to take the average of the second and third data points. It's there in the middle. So this is going to be the average of 2 and 3, which you can check is, of course, 2.5. So remember, median just has to do with the order of elements in a data set, not the actual sizes. So median isn't affected as much, or really at all, by really large or really small elements of a data set. So, in general, if the mean is quite a bit greater than the median, we say the data is skewed to the right. We're thinking right as big. So that means that there's lots of large elements in our data set that are kind of skewing it. If it's the other way, if X bar is smaller, quite a bit smaller than the median, then we say that the data is skewed to the left. And in a histogram, we can think of data being skewed to the right. It's going to look something like this. So you have kind of a normal symmetric looking data set, and then some more data to the right. So if we say the median of the data set is somewhere, I don't know, let's say, so we're going to have the middle, so maybe somewhere here. The mean is somewhere around here. The median is is smaller than the mean. So this is skewed to the right skewed, has this large right tail, and left skewed is going to look the opposite. So if we have kind of a symmetric looking data set, but then a bunch of smaller values like that, same idea, the median is somewhere around here, but the mean is going to be less than it. So let's say the mean is yellow here, and the median is green, just so that's a little more clear. This is a left-skewed data set, or skewed to the left. So when we're thinking of data sets, we can think of how the mean and the median differ, and that gives us an idea of if there's some especially large or especially small elements of a data set.